we analyzed insertion sort. And we looked at the best case and worst case. The one thing that I would like to emphasize is that the best case is always, the meaning of a best case is lucky case. So an input on which this particular algorithm is lucky, and it will not be doing very many operations. While a worst case is an unlucky input on which the algorithm will be performing many operations. Remember, algorithm analysis is all about counting operations. So this is lucky, this is unlucky. Now, lucky and unlucky, of course, is relative. So what's lucky for one algorithm may be unlucky for another algorithm. You know, as you may recall, for example, for quicksort, if the input is sorted and there is no randomization of the pivot, that's going to be a worst case. So what is best case for one algorithm is not necessarily a best case for all other algorithms. Now, last time, towards the end of the lecture, we started to introduce the notion of omega, big O, and big theta, and big omega. So we said that the big O is an upper bound. Big omega is a lower bound. And big theta is a tight asymptotic bound. So, for the worst case of insertion sort, and we are still reviewing what we did last time, for the worst case of insertion sort, we can easily calculate a lower bound by observing that this loop will get executed. Sorry, that's n minus 1. So I just caught an error. So it's an n minus 1, but in terms of order, it doesn't matter. So it's the same order. So this loop is order n, or this loop is bounded by order n. Right? So this means that this algorithm can never be any faster than n. So that's why we are saying lower bound of n. And we express this using the asymptotic notation by saying t of n is the running time of the algorithm. T of n, the running time of the algorithm. T of n, running time of the algorithm. Okay, so T of n is lower bound, which means it's equal to omega of n. Another way of looking at omega, you can view omega as being equivalent to greater than or equal. Now, in terms of an upper bound, we can say, okay, this loop is bounded by n. This loop, the number of executions of this loop, is going to vary depending on I. For a different I, this loop will be executed a different number of times. But the number of times of this inner loop will not exceed n anyway, because we are starting from I minus 1 to 0. And I minus 1 is going to be anywhere between 1 and n minus 1. So I minus 1 is a number in this range, and we're going from I minus 1 to 0. So this is definitely bounded by n as well. Bounded by n. So since both loops are bounded by n, we can say that the running time of this algorithm, T of n, equals big O of n squared. Again, big O is an upper bound, and you can think of it as less than or equal to. So we are saying that the running time of this algorithm, so far, based on the analysis that we have done so far, it's not going to exceed n squared. So without doing that summation that we did last time, remember the summation that we did last time, and that resulted in an order n squared, or in fact, the summation gave us t of n equals n minus 1 divided by 2. Okay, and this is what we expressed using the theta notation. This is theta of n squared. So this is absolutely of order n squared. So you can think of the theta as equal. So the point here is, before doing the summation, if we just stop here, we can say that, OK, based on a very quick analysis, without doing the summation or anything, we can say that the running time of this algorithm is going to range from n to n squared. It's going to be something between n and n squared. It could be n, it could be n squared, could be one of them, but it's not going to be any less than n, and it's not going to be any greater than n squared. Now, is this useful? By the way, for an algorithm like insertion sort, where you can actually do the precise analysis and compute the theta, omega and O are not useful. So it's, here we are only explaining the concept, but using big omega and big O is not useful here, because we can do the precise analysis. If you know the theta, you no longer need the omega and big O. It's like knowing that the price of something that you would like to buy ranges from $200 to $500. Knowing this range, this is a useful piece of information. But if you know that the price is exactly $400, you no longer need this. So why are we studying omega and O, big omega and big O then? Because there are algorithms that are hard to analyze. Sometimes there are algorithms that are hard to analyze precisely. So computing the theta, which is the most precise, running time that you can compute, is not possible. So in that case, you just bound it from below and bound it from above. You compute lower bounds and upper bounds, when the algorithm is so complex that you cannot do a precise analysis. Of course, this does not apply to insertion sort. Insertion sort is a very easy algorithm to analyze. It's only a matter of computing that summation. Okay, and sometimes using the big O and big omega, sometimes it's useful because there are certain parts of the algorithm that you don't have to analyze precisely. For example, if you have an algorithm like this, and you divide the algorithm into 3 sections that will be executed sequentially, and you say, OK, this section, I analyzed this section, and this section is theta of n squared. Now, if you analyze these other 2 sections, you don't have to analyze the other 2 sections to the theta precision. If you can say, for example, that this is O of n squared, and this is O of n squared. So there are 3 sections of the algorithm. I know that this is precisely theta of n squared. But this is something that is n squared or less. And this is something that is n squared or less. I don't need to know these exactly. I can easily say that the overall running time of the algorithm is going to be what? Theta of n squared. Because the order of these is going to be either the same or less. Okay. So this is where we use the big theta and big omega. You can argue about certain sections of the algorithm that you don't have to analyze exactly. You can either compute either a lower bound or an upper bound, and that can be useful. Okay. Okay. Now, I would like to emphasize something here. note that we are using this big omega and big O and big theta. We are using this to describe the worst case running time. One common mistake is to think of omega as the best case running time of the algorithm. No, omega is not the best case. The concept of omega and O, big omega, big O versus big theta, is about precision, is about the accuracy of the analysis that you are doing. So whether you use theta or O and omega, it's a matter of precision, how precise your analysis is. While best case versus worst case is a totally different concept. It's the concept of lucky versus unlucky. Two different concepts. This is lucky, this is unlucky. And the unlucky here, you can express it using these 2 bounds, or you can express it using the more precise tight bound. Okay, so it's a common mistake to think of omega as a best case. Okay, so here in fact we can say that the best case asymptotic complexity of this algorithm, T best case of n equals theta of n. So the best case is going to be, we know that it's going to be theta of n exactly. So, okay, so let me write it down. So, O omega versus theta is imprecise versus precise. While best case versus worst case is lucky versus unlucky. Lucky input versus unlucky input. Now another common mistake is to think that the best case performance of an algorithm happens when the input is small, or the input is an empty array or an empty list. No, this is not true. So best case has nothing to do with the size. Best case versus worst case has to do with the structure of the input, the nature of the input, lucky or unlucky. Whether it's an input that the algorithm will be performing lots of operations on, or very few operations. Okay, in all cases, we only care about large inputs. In algorithm analysis, we only care about large inputs. We never care about small inputs, because for small inputs, it's all algorithms are fast. Remember, if you just look at exponential, exponential is bad and slow. But 2 power 10, if n equals 10, 2 power 10, that's 1,000. 1,000 is nothing, because we estimated last time, we gave a rough estimate of 10 power 8. A typical computer can compute 10 power 8 operations per second. So this is 2 power 10, which is almost 10 power 3. So this is nothing. This is exponential, and it's still taking nothing, a small fraction of a second. Right? So for small input, we don't care, because all algorithms are going to be fast. We only care about large input. So best case is a lucky large input, and this is an unlucky large input. Okay. So any questions of these concepts? So these are very important concepts in algorithm analysis, and we will be using all of these concepts throughout the semester. Any questions on what's on the board? Okay, so one thing that I did not get the chance to talk much about last time is the arithmetic series. So last time, you know, we constructed this summation. We said, okay, for I equals 1, this algorithm will be doing 1 shift. For I equals 2, it's going to be doing 2 shifts. And for I equals n minus 1, it's going to be doing n minus 1 shifts. So, by the way, why are we counting the shifts and considering the number of shifts to be the asymptotic complexity of the algorithm? Why is the number of shifts and the asymptotic complexity of the algorithm refer to the same thing here?
Because shifts are the actual operations that I use to solve the.
But we are using other operations as well. So we are using this, for example, this compare operation. We are using this comparison. We are using other operations.
This will take more time.
It's what?
It will take more time to compute. It's like it will take less.
It will take more time. Yes, it will take more time. We will be doing more shifts than any other operation, right? In the worst case. So in the worst case, this is in the doubly nested loop. So we will be executing this shift. The number of executions of this is going to be greater than anything else. In fact, there is something else that is inside the loop and will get executed the same number of times. Even there is something that will get executed.
Comparison.
What's that? The comparison, yeah. So in fact, even though it's not shown here with this form of the code, maybe it's more obvious with the form that we showed last time, but the comparison is also done the same number of asymptotically. In fact, there will be one more comparison. Was the last comparison we will fail and we will not enter the loop. Right? By the way, when we exit this loop, what will the value of j be? If assuming that this condition was true all the time. Okay, so when we exit the loop, what will the value of j be when we exit the loop? No, in fact, it will be -1. J will be -1 when we exit the loop. Why is that?
It fails the condition.
Yeah, because it's the value of j that will make this condition evaluate to false. So whenever this evaluates to true, what will happen? We'll enter the loop. When it's true, we enter the loop. When it's false, we break out of the loop. We don't enter the body of the loop. So when we exit this loop, the value of j is going to be -1. So usually, to analyze the asymptotic complexity of an algorithm like this, basically you count the number of executions of the innermost loop, or whatever is in the innermost loop. So, and since we are looking for asymptotic complexity only, I mean, we can calculate shifts and compares as well, but this is going to only make a difference by a constant, right? So if we calculate both, that's going to multiply it by 2, and we don't care about constants in asymptotic complexity. So if we just calculate, if we count the number of shifts, that should give us the asymptotic complexity of the algorithm. Okay? Any questions on this? Okay, so now the running time t of n equals 1 plus 2 plus n minus 1. Now this is an arithmetic series. And let's see who remembers the formula for the arithmetic series. So the arithmetic series sigma x or sigma I, for I goes from 1 to x, that's equal to x times x plus 1 divided by 2. And I always propose a mnemonic for this, a way of remembering this, remembering this formula or deriving this formula. If you forgot the formula, don't memorize it. Just think of this example. If you are adding 1 plus 2 plus 3 plus 4 plus 5 plus 6. In this case, what's the value of x?
6.
X equals 6. Right? You are adding the numbers from 1 to 6. Now, how do I add these? I can add these by saying 1 plus 6 is a 7. 2 plus 5 is another 7. And 3 plus 4 is another 7. So how many 7s do I have? 3 7s. So 3 times 7. Now what's the relation between 3 and x? Yeah, it's half x. So this is x over 2. This is x over 2. And what's the 7? X plus 1. So in general, I have, x plus 2 pairs, x plus 2 pairs, and the sum of each pair is x plus 1. So each pair has a sum of x plus 1, and there are x over 2 such pairs. So this is just a proof. This is a derivation of this formula, but this applies to, there is a restriction on this analysis or argument. This applies under what condition? Only if it's even, right? This analysis assumes that x is even. So if x is odd, you will have a single item in the middle. So you'll have to add it. But then if you add it, you will still end up with the same formula. So even if you do it for odd and you add the single item, you will end up in the middle, that will not get paired with another number, and then you add it up, you will end up with the same formula. So this should be a very good mnemonic. If you forget the formula for arithmetic series, you can remember it. Okay, and we will be using the arithmetic series and the geometric series quite a bit in this course. We will do the geometric series when we get there. When we start analyzing trees, we will do the geometric series. Okay. Any questions? Okay. So in fact, in addition to big O, big omega, and big theta, we have the small o, which means, which is an, it's an upper bound, but it's an exclusive upper bound. So it's less than. It's equivalent to less than. By the way, this is just equivalence. You cannot simply replace big O with less than or equal. So it's conceptually, when you are comparing functions using the big O, it's conceptually similar to comparing numbers using less than or equal. But mathematically, you cannot just replace big O with less than or equal, or big omega with greater than or equal. And there is a omega, which is an exclusive lower bound. So it's equivalent to greater than. Now the point is, we can use these asymptotic notations to express the running time of algorithms, but we can also use them to compare functions. So we can say, for example, I think we are done with insertion sort now. So you can, for example, say n squared equals big O of n cubed. So again, this is like saying n squared has the same order of n cubed or less. So it's less than or equal. Okay, so this is a correct, it's a true statement. You can say n squared equals big O of n squared. So this is also correct because it's less than or equal. And you can say n squared equals big theta of n squared. So people usually use the big O more than the big theta, and in many cases people use the big O when big theta is more appropriate. So we use big theta when we have done a precise analysis. So sometimes people would do a precise analysis and they still use the big O instead of big theta. So this is like common practice. It's just the big O is more popular than the big theta, and people use it. Sometimes use it properly when it means less than or equal, and sometimes they use it when they should be using theta. But if they use the big O when big theta is the right notation to use, big O is never wrong. So when you analyze an algorithm and it's precisely n squared, you can say it's theta of n squared, and you can say that it's big O of n squared. You can say both, and they are both correct. This is more precise and makes a stronger statement and gives a more precise information. It's like asking someone how old are you, and they are 36, and they would say, I'm 36 or younger, right? So this is a true statement. They're 36, but if they say I'm 36 or younger, then this is still a true statement, but it's not as informative and it's not as precise. When they say I am 36, that's more precise. So when people use the big O, when they should be using the big theta, they're just like asking about a number, whether it's the age or the price, and someone tells you it's 36 or less, or this thing is $100 or less, but it's in fact $100. Okay, so this is what it means. So this is true as well. Now when you say n squared equals big omega of n, this is true. You can say n squared equals small omega of n. This is true. But can you say n squared equals small omega of n squared? No, because omega means greater than. Okay, so this is wrong. Now, if the running time of an algorithm is theta, suppose that t of n equals theta of n squared. Now, if we know this, then we know a very tight asymptotic bound, and in fact, we no longer need. We don't need, big O and big omega. But if we use them, it will not be wrong. So we can say t of n equals O of n squared. This is correct. You can say t of n equals O of n cubed. This is correct. And t of n equals O of n to the power 100. This is correct. Now, this is correct, but how useful is it? So it's not very useful. Right? So if you ask about the price of a smartphone, and someone tells you that the price of this smartphone is $5 million or less. The price of this smartphone is $5 million or less. Is this a true statement? Yeah, it's a true statement. Even if it's a cheap smartphone. Right? This statement is still true. But is it useful? No, it's not useful. So there are true statements that are not useful. And when it comes to bounding the running time of an algorithm, tighter bounds are more useful. Looser bounds are less useful. But they're still true. So this is, if we know that the running time of an algorithm is n squared, saying that it's O of n power 100, this is a true statement, but it's not a useful. It's not very useful. It's too loose. So tighter bounds are more useful. The tighter, the more useful. And the tightest is the theta. So whenever t of n equals theta of some function f of n in general, if the running time of an algorithm is known to be theta of f of n, then we can also say this implies that t of n equals big O of f of n, and t of n equals big omega of f of n. In fact, the implication goes in both directions. So saying that t of n equals theta of f of n implies, so let's put it this way. If t of n equals theta of f of n, this implies that t of n equals big O of f of n and t of n equals big omega of f of n, so that the lower bound and the upper bound are f of n. And if you can calculate the upper bound and the lower bound, and they're both equal to f of n, this implies that t of n equals theta of f of n. Okay? Yeah, so if the price of a certain product is $100, if the actual price is $100, you can say that the price is less than or equal 100, and it's also greater than or equal to 100. And if someone tells you that the price is less than or equal 100 and is greater than or equal 100, then that implies that the price is exactly 100. Okay? Okay. Questions on this? Okay, so now how do we compare two functions? In fact, we have a definition. In this course, we will adopt the limit definition of asymptotic complexity. So given two functions, f of x, or let's say f of n, because we are in algorithm analysis, f of n and g of n, now in order to compare them and figure out the relation between the two functions, the asymptotic relation between the two functions, we should take the limit at infinity. The limit of what? What do you think should be in order to compare them? The limit of, as n goes to infinity, but the limit of what? The limit of f of n or the limit of g of n? So like I'm comparing n squared and n.
You divide one by the other.
Mm-hmm.
You divide one by the other.
Yeah, exactly. So you take the limit of the ratio. If you take the limit of the ratio as n goes to infinity, then that will tell you the asymptotic relation between the two. So given two functions, f of n and g of n, if limit as n goes to infinity of f of n divided by g of n equals 0, what does this mean? It means which one is smaller and which one is larger. So this means that the one in the numerator is smaller and the denominator is larger. So as we go to infinity, this is smaller and this is larger. So this means this implies that f of n equals, so it's less than, so less than is small o. Yeah, so this is 0, so that you don't think it's o or something. F of n equals small o of g of n. Or you can say g of n equals, or you can say that g of n is
Greater or equal.
yeah, it's greater than. So g of n is omega of f of n. Right? What else is true? What other statements can you make using the asymptotic notation here? Can we apply the big O? Well, the big O is less than or equal. So whenever the small o applies, the big O is going to apply. So we can apply f of n equals big O of g of n. And we can apply g of n equals big omega of f of n.
Wouldn't that equal 1 if they're equal?
If they are equal.
If they are what?
They're equal, then it would equal 1, wouldn't it? The result.
If they are equal,
It wouldn't be 0. It would be 1.
The limit.
The limit.
the limit will be 1.
Yes.
If they are equal,
Yes.
yeah. So, well, if they are equal, the limit will be a constant. And in that case, the relation will be what?
Theta.
Theta. Yeah. So if the limit is 0, we get this. If the limit of n as n goes to infinity of f of n divided by g of n is k, where k is a non-zero constant, then this will imply that f of n equals theta of g of n. So if the limit of the ratio at infinity is a non-zero constant, then they're both of the same order. But we can also make other statements here. We can say that f of n is also big O of g of n. So let's mark the most precise statements. So these are the most precise statements. So these are looser statements. These are less precise, but they're still true. So this is true, but less precise. Now this is the most precise statement. But we can also say that f of n equals big O of g of n. And we can say f of n equals big omega of g of n. Right?
G of n.
Can we say this?
G of n should be.
So they're of the same order. So it's like n squared, 4n squared and n squared. 4n squared and n squared are of the same order. So if f of n, so let's give a specific example. So an example of this, if f of n equals n and g of n equals 2n squared, then this is this case. The ratio, the limit of the ratio, the limit of f of n divided by g of n, in this case as n goes to infinity, is the limit of n divided by 2n squared, and the limit of n divided by 2n squared, or the limit of 1 over 2n, and this limit equals 0. So this is an example of this case. So in this case, all of these apply. So you can say that the f is small o of the g, or the g is a small o of the f, or you can use the big O and the big omega. Now an example of this, for this case, so this is case 1, this is case 2, case 1. An example of case 2 is just two functions of the same order. for example, n squared and 4n squared. Well, this is f of n, or let's write it properly. F of n equals n squared, and g of n equals 4n squared. In this case, the limit of f of n divided by g of n as n goes to infinity is the limit of n squared divided by 4n squared. And this is 1 over 4. So the limit of 1 over 4 equals 1 over 4, which is a non-zero constant. So this is case 2. So in this case, you can say that the relation is theta. They're both equal in order. You can say big omega, so big O, big omega. And also you can say, what else can you say? You can say that g of n equals, you can say it's equal to O of f of n. And you can say that g of n equals big omega of f of n. All of these are true. But this is the most precise and the strongest statement that we can make, okay, about them. So this is an example of case 2. Now case 3, limit of f of n divided by g of n as n tends to infinity is what? So it could be 0 or a constant or infinity. So if the limit equals infinity, then if the limit is infinity, then the numerator is greater. So f of n equals small omega is greater than g of n. Or you can say it backwards. You can say g of n equals what? Small o of f of n. But since the omegas apply, the small omega and the small o, you can also use the big omega and big O, right? So you can also say, now this is precise, this is precise. Now when you use the big O, it's looser, but it's still true. So you can also say f of n equals big omega of g of n. So you can say it's greater than or equal, even though we know that it's greater than. And you can say g of n equals big O of f of n. Okay. So this is about asymptotic notation and the definition of the small o and small omega. This is one general method for comparing two functions. So basically, to compare two functions, take the limit of the ratio as n goes to infinity, and then look at the limit. If the limit is 0, you have this. If the limit is a non-zero constant, you get this. If the limit is infinity, you get this. Okay? Questions? Okay, so
Question.
yeah.
Going back to the insertion sort example, you said that, so O of n is n squared, and then omega of n is n. Why is theta of n n squared and not n?
Because we did the precise analysis, and the precise analysis gave us n squared. It did not give us n. So the precise analysis is the summation in this case.
Oh, okay.
So we did the summation, and the summation gave us n squared. So it turns out that the precise value of the running time, of the worst case running time, is order of n squared. And we expressed that using the theta. Okay, yes?
Is there no upper bound or lower bound for the best case?
Oh, for the best case? In theory, yes, you can. For the best case, you can use upper bound and lower bound, but usually the best case is an easy case for which we know the theta. You know, the best case, because it's a lucky case, and it's a lucky case because it's usually very simple, and for which we already know the theta, so there is no reason to use the big O and big omega. But in theory, yes, you can do that. In fact, you know, when you say that the t best case equals theta of n, you can also say that t best case of n equals big O of n. This will also be correct. And also t best case of n equals big omega of n.
Is there a problem that has a different upper bound and lower bound?
For the best case,
Yeah.
it depends on how precisely you do the analysis. I mean, an upper bound and a lower bound, basically for any algorithm, there is an infinite number of upper bounds and an infinite number of lower bounds. So if if n is a lower bound, then any function that is smaller than n is going to be a lower bound as well. And if n squared or n cubed is an upper bound, anything that is greater than n cubed is going to be an upper bound. So there is an infinite number of possible upper bounds and an infinite number of possible lower bounds for any algorithm. And remember, and among these bounds, we are always interested in the tightest ones, in the ones that are, we want them to be as tight as possible. Yeah.
So if the worst case for like quick sort is big O n squared, then why do we always say that n log n is that?
Oh, okay. So I will defer answering this until we get to quicksort, because we will do quicksort and we will analyze it. But a short answer for now is that, yes, the worst case for quicksort is n squared, but that worst case is extremely unlikely to happen in practice. Okay, so it's very rare. So in most cases, quicksort behaves as an n log n algorithm, but we will analyze that in detail.
When you say for most cases, are you saying like the average case?
It's even more than the average case. Yes, it's the average case, but it's like the vast majority of the cases, not only the average case. So the average case is not a very strong statement. It's just the worst case is extremely unlikely, especially if you randomize the pivot. Okay, but we will analyze it in detail. Okay, any questions? Okay, so now let's look at the different functions that we use in algorithm analysis. So usually we have log n, then we have n, and we have n log n, we have n squared. So when we go in this direction, the functions are growing faster, and when the function is growing faster, it's giving a slower algorithm. So faster growing function and slower algorithm. Okay. So this is, faster growing function gives a slower it's logic. So who can explain this logic? Why does a faster growing function give a slower algorithm? When we go in this direction, for example, n squared is a faster growing function than n, but an algorithm with a running time of n squared is slower than an algorithm with a running time of n. So who can explain this? Yeah.
Because the faster growing function is a function of the number of steps of the algorithm. So the higher order ones means it's just going to take longer. 'Cause there's one.
Yeah, exactly. So when we say faster growing function, we mean a function that the number of operations that this algorithm is going to perform is growing, so it's increasing. And when the number of operations increases, that means a slower algorithm. So, in fact, we can. So let's draw. Okay, so this is n, and this is n squared. So n squared, the function n squared grows faster. What does it mean grows faster? It means that for the it goes, the number of operations increases. So if we look at, if we look here, for this value of n, some some n, certain n, for this n, the number of operations performed by n is less than the number of operations performed by n squared. And if we increase n, the difference is going to even get bigger and bigger, right? So I always like to emphasize this because I was once teaching this. In fact, a long time ago, I was teaching this as a TA, and I was sometimes, thinking in the function, in the growth of the function, and saying that it's faster. And sometimes I was thinking in my mind in the algorithm and saying that it's slower. And I wasn't explicitly saying this. And one student got confused. So one student asked me, is n squared faster or slower than n? Well, then I had to explain it. The function n squared goes faster than the function n, but an algorithm whose running time is n squared is a slower algorithm than an algorithm whose running time is n. Okay? Okay, now we have n squared. We have n cubed all the way to n power k, such that k is a constant. Then let's draw this line. So let's draw it in red. Then we have, 2 power n, 3 power n, a power n. So what do we call these functions?
Exponential.
So these are exponential. So this is the this is the polynomial. So this red line defines the boundary between polynomial and exponential. So in fact, if the running time is in the polynomial range, the problem is considered tractable. So if there is an algorithm that has a polynomial time algorithm, it's tractable, which means it's relatively easy than a problem whose that does not have a polynomial time algorithm, so it's intractable. And remember that when we say tractable or intractable, this is a property of the problem, not the algorithm. Okay. So a tractable problem is a problem that has a polynomial time algorithm. An intractable problem, or a problem that does not have a polynomial time algorithm is considered intractable. So this is a property of the problem, not the algorithm or the function. Okay. Now, what about n factorial? Where does it fit on this map?
Lower.
Yeah, so it's even larger than a power n. Right? Because n factorial, if you compare, for example, 2 power n is 2 times 2 times 2 n times, while n factorial is 1 times 2 times 3 times 4. So if you look at it this way, it will become obvious that factorial is greater than exponential, because this is a constant that you are multiplying by itself n times, while n factorial you are multiplying by larger and larger numbers. Okay. And what is even larger than n factorial is n power n. So n power n is n times n times n. So this is even larger. Okay. So now let me ask you this. What about square root of n? Where does it fit?
Log n.
Is it greater or smaller than log n? Smaller than log n. No, it's larger than log n. So square root of n is going to fit here. Okay, so how do we know this? In fact, we can calculate the limit. If you are in doubt, you can calculate the limit. And I'm not going to do square root of it. I'm going to do even smaller than n. So the limit of log n divided by n power 0.1. So 0.1 is this smaller or larger than the square root?
Smaller.
Obviously, it's smaller as n goes to infinity. So how do we calculate this limit? How do we calculate this limit?
Good question.
Okay. So any clue?
Nope.
How? Okay, so what, can you think of any useful rule that can help us with this?
Some identity with log n.
Well, yeah, log n we can, okay, yeah, we can convert it into something else. But in general, when you have, when you are calculating the limit of two functions and each one goes to infinity, both of them go to infinity, you can use L'Hopital's rule, right? Yeah. So do you remember L'Hopital's rule? Okay. So you take the derivative of the numerator and the derivative of the denominator. But in order to take the derivative of log n, what's the derivative of log n?
1 over n.
No, but that's the derivative of ln n, the natural logarithm. So d ln n by dn equals 1 over n, right? But that's for the ln, for the natural logarithm, which is a different base. But in fact, when you convert an algorithm from one base to another base, how do you do the conversion? So let's try to remember this. This is some basic math that we will be using. We will not be doing a lot of math in this course. So this is this course is going to emphasize. It's going to take an intuitive approach to algorithms. So we will definitely emphasize the intuition and the practical aspect of algorithms. But we will need to do a little bit of math. So, for example, if you have log n or log n base or log x base a, this is equivalent to log x to some other base, log x base b, divided by log a base b. Now, what does this? Why is this useful here? Because in fact, this can be used to convert from one base to another, right? So you can convert from one base to another. So this gave you, this is log x base a. You converted it to log x base b, and here you divided by log a base b. Now, what can we say about log a base b? What can you say about it? So in that, we are doing asymptotic complexity.
Base 2.
So this is a constant. Remember now, when we are doing algorithm analysis, constants don't matter. So we don't care about the actual values of the constants. Anything that we can determine is a constant, we can basically ignore it, because constants make no difference when we are doing asymptotic complexity. So now, in order to convert log n to ln n, we will multiply by some constant. We don't care what that constant is. We can calculate it if we want, but we are not interested for the sake of calculating this limit. So this is going to be equal to k ln n, some constant, divided by n 0.1. Now we can we can take the derivative of the numerator and the derivative of the denominator. So this is going to be equal to limit as n goes to infinity of the k ln n, or we can go ahead and calculate the derivative already. So d of ln n by d n equals 1 over n. So here the limit is going to be 1 over n by k. So k over n divided by, what's the derivative of n.1? It's 0.1 n 0.1 minus 1, which is minus 0.9. Right? So this is the derivative of this, and this is the derivative of the denominator. So in fact, this is going to be equal to k. You can put in the denominator, and this is minus 0.9, so you can put it in the numerator. So in fact, this is k prime. You can say k prime because it's k divided by 0.1. Remember that I don't care about constants in asymptotic complexity. So k prime equals k divided by 0.1. And this is n 0.9. And this is k prime divided by n power 0.1. And what's this limit? So you have the n in the denominator, and we're going to infinity. So what's the limit?
0.
0. The limit is 0. So what does this tell us? It tells us that log n is smaller than any polynomial. So even if we replaced n.1 by n.0001, we will still get something here. We'll get n.0001 in the denominator, and the limit will still be 0. Right? So in conclusion, the log is smaller than any polynomial, no matter how small the exponent is. So log is smaller than any polynomial, no matter how small the exponent is. Okay, so log n is greater than square root of n. Now, what about log n squared? So log n squared, where will this fit? Is it larger or smaller than log n?
Larger.
Yeah, so it's larger than log n. And you can also prove that it will still be smaller than any polynomial. So it's log n squared is going to be here. It's larger than log n and smaller than square root of n. What about log n?
Smaller than log n?
Yeah, smaller than log n. Log n. So log n squared, when you square log n, you are multiplying it by a log. You are multiplying it by something small, but this small thing is growing. It's going to infinity. So in fact, at infinity, it will be infinity. So when you are multiplying log n by log n, when log n is multiplied by log n, this makes it larger. When it's multiplied by log n, it gets larger. But when you take the log of log n, when you take the log of something, you make it smaller. Okay, so log n is smaller than this argument here. So when you take the log of something, you make it smaller. So that's why log n is smaller than log n. Okay. Okay. So now these are the functions that we will be using most of the time. Maybe we should also prove that any polynomial is going to be smaller than any exponential. So if we look at, if we take the ratio between a polynomial and an exponential, what should that ratio be at infinity? The ratio between any polynomial and any exponential should be 0 or infinity?
0.
No, the ratio between a polynomial and an exponential. So what's the limit of n power k? So k is a constant here, divided by 2 power n.
0.
And why is that? So in order to calculate this, so this is a polynomial, so we can apply L'Hopital's rule. So we know how to derive a polynomial, but in order to derive this 2 power n, we'll have to convert it into, again, an exponential with a natural base. So 2 power n is equal to 2 power n, e power n ln 2. And this is something that you can prove easily, because e ln 2 power n, so e ln 2, so these are inverse functions, so e ln 2 is going to be, so this is n. So e ln 2, two inverse functions. So this is going to be 2 power n. So this is 2 power n is equal to e n ln 2. So this limit is equal to the limit of n power k divided by e ln n ln 2. Now note that ln 2 is a constant. Ln 2 is a constant. Now to derive, this is equal to limit as n goes to infinity of k n k minus 1 divided by some constant multiplied by e n ln 2. Of course, this is a different constant, k prime. Okay? Now, if we keep deriving this, so if we keep taking the derivative, what will happen to this? So if we keep taking the derivative of this polynomial, eventually we will get to what? To a constant, right? Or even 0. So we'll get to a constant. And if we keep taking the derivatives here, what will happen to this exponential function? Will it ever disappear?
No.
No, if we keep taking the derivative, the exponential will not disappear. So we will get a k prime, double prime, e n ln 2. And let me remove this to avoid confusion. So what's this limit? So basically by taking the derivatives, this will go away, the polynomial will go away, but the exponential will not go away. It will stay. And which means that the limit is 0. What does this mean? It means that the polynomial, any polynomial is smaller than the 2 power n exponential. In fact, this will apply to any exponential, even if even if you change the base from 2 to 3 or 4 or anything, you can do it in general, because this will only affect this constant. So it will be, instead of ln 2, it's going to be ln 3 or ln 4 or ln 5. So it's going to only affect this constant. So any polynomial no matter how high its order is smaller than any exponential. Okay? So any polynomial is smaller than any exponential. So that's why, in algorithm analysis, it's, polynomial is not as bad as exponential. Faster growing function gives a slower algorithm. So intuitively, what this means is that the derivative is the rate of change, the rate of growth. So the fact that the derivative of a polynomial is a lower order polynomial, it means that the growth rate of a polynomial is smaller than the polynomial itself, because it's a lower order polynomial. So the derivatives expresses the growth rate, while the derivative of an exponential is still an exponential. So the growth rate is still exponential. So the growth rate of n cubed is n squared, a lower order polynomial, while the growth rate of e power n or 2 power n is still 2 power n. It's still yet another exponential. So that's why the polynomial will go away, but the exponential will not go away. And this means, this is very significant in algorithm analysis. And that's why it draws the borderline between what is considered relatively fast and what's considered hopelessly slow.